What if? What if everything we thought we knew about fundamental physics, like why things seem to get heavier the faster they move, or why clocks appear to slow down when they're in motion, what if all that math, the stuff that's incredibly accurate, was actually, well, fundamentally misinterpreted? At a deeper level, I mean. Imagine a universe where time slowing down isn't really what's happening at all. Maybe it's something else entirely, something more intricate. Welcome to the Deep Dive. Today we are strapping in for a really mind-bending journey, a deep dive into the very fabric of reality, you could say. We're tackling this groundbreaking new paper. It's titled Relativity 2.0, Coherence Dynamics in the Finsler Coherence Hyperfractal Phase Space. Quite a title. It's by Philip Randolph Lillian from the Holonomics Institute for Coherence Physics. Yeah. Now, let's be really clear right from the start. This isn't about trying to debunk Einstein or saying special relativity was wrong. Not at all. Einstein's work, still absolutely brilliant, an unparalleled mathematical description of what we see, what we observe. But this paper, it's proposing something different.
A profound ontological upgrade to special relativity, like a whole new way of understanding the underlying reality that causes those effects we observe. So our mission today, if you choose to accept it, is to unpack this incredibly complex framework. It's dense, but fascinating. We want to reveal its surprising core insights, hopefully give you some genuine aha moments, things that might just change how you think about physics. We'll explore how it could radically reshape our view of reality itself and maybe even, astonishingly, future technology. You're going to hear how this new theory reframes key concepts, things like mass, time, the speed of light. It replaces some of the more, let's call them slightly mystical interpretations of classical relativity. The idea of space itself bending or time really slowing down. This paper suggests a more grounded view based on coherence. And here's why this isn't just some abstract thought experiment for physicists in labs. This paper directly points towards potentially revolutionary new experimental paths and new technologies. We're talking tangible possibilities, like maybe mitigating relativistic mass growth.
That's a huge hurdle for interstellar travel. Right. And maybe even entirely new kinds of propulsion. So if you've ever wondered about the true nature of reality, or maybe dreamed about faster than light travel, well, stick with us. This is going to be a wild ride into what might be the future of physics. Okay, let's unpack this. To really get where this new thinking is coming from, I think we need to set the stage first, do a quick rewind. Before Einstein, turned everything on its head, physics operated under something called Galilean invariance, part of classical Newtonian mechanics. Can you take us back there? Just quickly explain the core ideas. What did we think we knew about motion and time back then? It felt pretty intuitive, didn't it?
Absolutely, yeah. Galilean invariance was the standard model for centuries, and it felt very intuitive, very common sense for the world we experience directly. First off, it stated that the laws of motion are exactly the same in all inertial frames. Now, an inertial frame, just for everyone listening, is basically a reference point that isn't accelerating, it's moving smoothly, or maybe it's just sitting still. So think about being on a perfectly smooth train, moving at a constant speed. If you do a physics experiment there, like dropping a ball, the result should be exactly the same as if you did it standing on the ground. The laws of physics don't suddenly change just because you're moving uniformly. Second, and this is really crucial for where we're going today, Galilean invariance assumed that time is absolute, completely universal. That meant everyone, everywhere, experienced time in exactly the same way. A second was a second, period. Whether you were here on Earth or zooming through space, there was no concept of time stretching or shrinking or slowing down for anyone. It was just this universal metronome ticking away identically for everything. And third, velocities were simple. They just added up linearly. It's how we instinctively think about it, right? If you're on that train moving at, say, 100 kilometers per hour, and you throw a ball forward relative to the train at 10 kilometers per hour, someone standing on the ground would just see that ball moving at 110 kilometers per hour. Simple addition. 100 plus 10. It was all very neat, very logical. And for hundreds of years, it worked perfectly for describing pretty much everything they could measure, from falling apples to planets orbiting the sun.
Right? Beautifully simple. Made perfect sense for everything you could see and touch in everyday life. But then came light. And light, like it often does in physics, just threw this huge wrench into that elegant intuitive system. The Michelson-Morley experiment back in the late 1800s, it famously showed that light speed just didn't play by those rules. It didn't add up like the ball on the train. What was the massive puzzle there? The really unsettling thing that experiment revealed? Why did it shake physics to its core?
Oh, the Michelson-Morley experiment in 1887 was, it was a genuine crisis point for physics, no exaggeration. See, for decades, scientists figured light, being a wave, had to travel through something, some kind of medium. They called it the luminiferous ether. an invisible substance filling all of space, supposedly. And if this ether existed, well, the speed of light should change depending on how Earth was moving through it. Kind of like a boat's speed changes if it's going with the river current or against it, right? So as Earth orbits the sun, its speed relative to the stationary ether should be changing all the time. And so the measured speed of light should change too. But here's the kicker. Michelson and Morley built this incredibly sensitive device, an interferometer, to detect this difference. And no matter how they oriented it, no matter what time of year they did the experiment when Earth should be moving differently relative to the ether they found, nothing. The speed of light always measured the exact same value, roughly 300,000 kilometers per second. Always. It was completely baffling. It flew directly in the face of that simple Galilean velocity addition. Light just didn't seem to care how fast the observer or the source was moving. This result was a profound mystery. It challenged the very ideas of absolute time and space that had been the foundation for 2 centuries. Physicists were left scratching their heads, facing a paradox that defied all common sense.
And that baffling paradox, that constant speed of light no matter what, that's exactly what paved the way for the next huge leap, wasn't it? Einstein's special relativity in 1905. So Einstein, faced with this light speed puzzle, didn't try to find the ether. He basically said, okay, let's accept the experiment. Light speed is constant. And to make that work, he had to replace Galilean invariance with something called Lorentz invariance. Can you break down the 2 core postulates of special relativity that came out of that?
Exactly. Einstein's genius was really in taking those experimental results seriously at face value and then building a whole new framework around them, even if it meant ditching some really deep-seated intuitions about space and time. So his special relativity, or SR, it rests on just 2 postulates. They seem simple, but their consequences are enormous. Both are tied into Lorentz invariance. First postulate. The speed of light in a vacuum, which we call c, is constant for all observers. Doesn't matter how fast the light source is moving, doesn't matter how fast the observer's moving, it's always c. This was the direct, elegant answer to the Michelson-Morley problem. C is a universal speed limit, a universal constant, full stop. Whether you're standing still, flying in a jet, or in a hypothetical rocket nearing light speed, if you measure the speed of light in a vacuum, you get the same number, always c. Second postulate. The laws of physics are the same for all observers in uniform motion. So for all those inertial frames we talked about earlier, this basically extends the old Galilean idea that physics works the same on the train as on the ground to all physical laws, including electromagnetism. And critically, it incorporates that first postulate, the constant speed of light. It means the universe doesn't play favorites. The rules are the same for everyone moving at a steady speed. Now, from just those 2 seemingly simple postulates, you get all the famous, often counterintuitive consequences of SR, like time dilation. Moving clocks tick slower relative to stationary ones. So the famous twin paradox, one twin zooms off in a rocket, comes back, and they've aged less than the twin who stayed home. That's real. And you get length contraction. Moving objects appear shorter in the direction they're moving. Again, not an illusion, but a real physical effect. These effects aren't just weird quirks. In SR, they're fundamental. They're baked into the geometry of space-time itself. Space and time aren't separate and absolute anymore. They become interwoven into this 4-dimensional fabric space-time that can stretch and distort precisely in order to ensure that the speed of light, c, remains constant for everyone. And this framework became the absolute bedrock for nearly all of 20th century physics. From immersion, nuclear energy, particle physics, right up to the GPS in your phone relying on relativistic corrections, it fundamentally changed how we see reality.
Right, so for, over 100 years now, our whole picture of the universe, from tiny particles to huge galaxies, has really hinged on c being that ultimate speed limit. And crucially, the ultimate constant. It's a really strong foundation, backed up by countless experiments and technologies. Pretty solid ground, you'd think. But then along comes this new paper, Relativity 2.0, by Philip Lillian. And it adds this really deep, almost philosophical question. Is Lorentz invariance, that bedrock constancy of c, is that really the deepest constant in the universe? And Lillian argues, no, which is a pretty bold thing to say considering how successful SR has been. So can you unpack the core critique here? What does the paper mean when it calls SR's reliance on Lorentz invariance a relational layer assumption? That sounds complex.
It is a big leap, yeah. And it forces us to think about physics in a fundamentally different way. The paper isn't saying SR's math is wrong. It emphasizes the math works brilliantly to describe what we see. But it argues that SR's ontological interpretation's explanation of what's fundamentally real might be incomplete. When it calls Lorentz invariance a relational layer assumption, it means SR treats the geometry of spacetime, the metric, as the primary thing, the fundamental thing. It's saying the ultimate constant, C, is a property of how things relate to each other within that spacetime geometry, how intervals are measured, how speeds combine, things like that. Let me try an analogy. Imagine you're watching ripples on a pond. You can describe them perfectly, their shake, their speed, how they interfere. SR is fantastic at describing those ripples. It gives us the perfect math for their behavior. But this paper suggests that by focusing only on the ripples, the relations, the geometry, SR might be missing the deeper cause. You know, the stone that got dropped in, or the fundamental properties of the water itself that allow those specific ripples to form. So, Relativity 2.0 argues that spacetime geometry, the stage SR plays out on, isn't the bedrock. It actually emerges from deeper, more fundamental ontological structures. It's like focusing on the movie projected on the screen without asking about the projector or the film itself. SR describes the movie. This paper wants to understand the projector.
Okay, I think I'm following. So SR says spacetime bends and stretches to keep square constant, but maybe doesn't give a deeper reason why it does that. It just is that way. And the paper calls this relational mysticism. Like, it works, it's mathematically sound, but the underlying cause remains a bit magical, almost. So if Fairsby isn't the true ultimate constant, the anchor for reality, then what is, according to this new framework? That's the million-dollar question, isn't it? Could change everything.
You've nailed the essence of the critique. That relational mysticism comes from SR describing what happens time dilates, mass increases, without offering a deeper, pre-geometric sort of causal mechanism for why spacetime itself behaves this way. It's postulated, not derived from something more fundamental. And this is exactly where Relativity 2.0 drops its bombshell. It's a really revolutionary core concept. The true fundamental invariant isn't C. It's something the paper calls hypergravity coherence. This is a radical rethinking of the ground state of reality. The paper formally defines something called omnilectic invariance. Let's try to unpack that. It's defined as the irreducible identity of this hypergravity coherence field. Imagine the universe, all of existence, permeated by this absolutely fundamental field. This field, the hypergravity coherence field, is described as being utterly unchanged by any kind of asymmetry or variance, even across different universes, if they exist. It's the absolute baseline. It exists before and independent of any dimensions, any symmetry breaking, any of the physical constants we usually talk about. Think of it as the deepest possible layer of reality, pure potential, undifferentiated being, almost. It has no metrics, no geometry as we know it, no change within itself. Mathematically, it's treated as just H, an invariant background functional, pure, unchanging potential. Now contrast that. Lorentz invariance in SR holds H steady. The older Galilean invariants tried to hold absolute space and time steady. Relativity 2.0 says no. The only truly unchanging thing, the only absolute invariant, is this omnilectic hypergravity coherence field. Everything else we observe, particles, forces, space-time geometry itself, and derived constants like stat, they aren't fundamental in the same way. Instead, they're all variables. They emerge from what the paper calls its symmetry reduction cascade, processes that differentiate and create structure out of that pure, coherent state, H.
Wow, that's a profound shift. So instead of a universe of fixed laws in a stretchy space-time fabric, we should maybe picture it more like a vast, infinitely coherent symphony, like a pure, perfect tone. And this hypergravity invariance, HH, is that fundamental tone. Always there, perfectly coherent, never changing. And everything else we see and measure, particles, forces, space-time, even the speed of light time, is just a variation, a complex chord, or maybe even a bit of dissonance, built upon that original perfect note. They're all derived effects, manifestations of this deeper constant, rather than being constants themselves. That's actually quite a beautiful image.
It is, and it's intended to provide a much cleaner ontological picture, a clearer hierarchy of reality. To really get a handle on how this emergence works, the paper lays out a layered ontology. Think of it like peeling an onion to get to the core. It describes three main tiers, which are themselves part of a larger context called the Unified Coherence Theory of Everything, or UCTE, but let's focus on these three main layers for now. At Tier 1, the absolute base, we have omnilectic hypergravity invariance, H. This is the deepest reality. Pure symmetry. No variance, no difference is even possible here. All potentials, everything that could possibly exist, are just co-present in perfect, undifferentiated coherence. The paper calls it the irreducible substrate of being. It's the fundamental ground from which everything else arises. You can't measure anything in H because there's nothing to distinguish or measure. It's pure potentiality. Mathematically, just that invariant background functional, the silent, unchanging source. Okay, moving down a level, we get to Tier 2. Asymmetry A. This is where things start to get structured, where difference begins. Here, things called coherence reduction operators come into play. These operators effectively carve structure out of that pure, undifferentiated H. This is the birth of variance. The very first introduction of distinguishability, the ability to have properties, to measure differences. Examples of these fundamental asymmetry operators are things like chirality, left-handedness versus right-handedness, quantum spin, electric charge, maybe even the dimensional breaks that give us our 3+1 dimensions of space and time. Mathematically, you can think of it as operators AI acting on H to produce a structured state, S equals AH. It's like a sculptor starting to chip away at a block of marble, creating form. And finally, at Tier 3, we have variance V. These are the results, the measurable residues of that Tier 2 asymmetry acting on Tier 1. These are the actual physical phenomena we observe and measure in physics labs and everyday life. Speeds, masses, redshift, blue shift, clock rates, field strengths, all that stuff. These are the observables that both Galilean and special relativity focused on describing. In this framework, these observables O, or what you get when you measure SOAOMS, it's the finished sculpture that we can now see, touch, and measure.
Okay, so if I'm getting this right, those big debates physicists have had, like, is the speed of light truly constant or could it vary? Those are basically arguments happening way down in Tier 3. They're arguing about how the variance behaves, how the sculpture looks from different angles, maybe, but they aren't necessarily questioning the deeper asymmetry in Tier 2 that produced the variance, let alone the ultimate invariant source in Tier 1. So this layered view kind of absorbs those debates by putting them in context.
Exactly. That's a perfect way to put it. Let's use the light speed debate as a concrete example of how this layered view works. Tier 1. Omnilectic hypergravity invariance, H absolutely unchanged. It sets the stage for what variance even means. It's the ocean itself. Tier 2. Asymmetry, A. Here, different programs or sets of asymmetry operators can act on H. These different programs can lead to different rules for how coherence behaves, different dispersion relations maybe. Think of it as different ways the stone can be dropped into the pond, creating different initial conditions. Tier 3. Variance, V. This is where observers measure the results, the ripples. Depending on the Tier 2 program and the measurement context, observers might report constant C. That's what SR describes so well in our universe's vacuum. Or they might report variable C, maybe under different physical conditions, or if light is traveling through a medium, or perhaps even in hypothetical alternative universes with different Tier 2 rules. All these observations, constant C, variable C, are just different variance behaviors, different ways the ripples manifest, all arising from the same deeper Tier 1, Tier 2 stack. It's like measuring a wave's height versus its frequency. Both are valid descriptions of the wave, Tier 3, but neither is the fundamental ocean, Tier 1, or the initial splash, Tier 2. This hierarchy is powerful because it helps avoid what the paper calls category errors, mistaking an effect, like SU being constant in a vacuum, for the fundamental cause. It shifts the focus from just describing what happens to understanding why it happens, tracing it back to the fundamental asymmetry programs acting on the ultimate invariant. Variance is symmetry made measurable.
That really does shift the perspective. Instead of just focusing on the ripples, we're asking about the water and the stone. Moving from description to cause, ontologically speaking, that feels much more complete. Okay, so this is where it gets really different from standard physics, right? SR says velocity is the key driver. You go faster, effects get bigger, simple cause and effect. But Relativity 2.0 throws that out. The core dynamic isn't velocity anymore, is it? It's this coherence coupling idea.
No, it's not velocity directly. This is definitely one of the most radical breaks from standard SR, and maybe the most important one. In Relativity 2.0, the fundamental driver of what we call relativistic effects, mass increase, time dilation, all that is coherence coupling to hypergravity. So those phenomena aren't caused directly by how fast an object is moving through space. They're determined by how coherent or how incoherent that object or system is with that fundamental hypergravity field we just talked about. It's about the quality of its connection to the bedrock reality. To make this quantitative, the paper introduces two really key concepts. First, the coherence ratio, C. It's basically a number, a scalar value, that tells you how strongly a system is coupled, how in sync it is with hypergravity invariance. If C equals 1, that's perfect coherence. Full connection, perfect alignment. If C equals 0, that's total incoherence. The connection is completely broken. Second, there's the coherence gamma, written as Eboshio with a subscript C, arch C. This is the Relativity 2.0 counterpart to Einstein's Lorentz factor, the gamma you see in all the ACR equations. But its definition and meaning are totally different. In Relativity 2.0, coherence gamma is defined simply as local C equals 1C, just 1 divided by the coherence ratio. This simple formula holds the key. As a system loses coherence, meaning C gets smaller and approaches 0, its coherence gamma gets bigger and bigger, heading towards infinity. And that's what drives the magnitude of the observed relativistic effects. Less coherence means bigger gamma means bigger effects.
All right, so if it's not just velocity causing these effects, then what does change this coherence ratio C? How do we end up observing things like mass increase or time shifts if they aren't just about speed? What's the actual physical process that makes a system lose coherence?
And that is the absolute linchpin connecting the old view to the new. The critical insight in the paper is this: acceleration induces incoherence. When you accelerate an object, meaning you change its velocity, speed up, slow down, or change direction, you are actively disrupting its smooth, stable coherence with the fundamental hypergravity field. It's not about space-time bending in some abstract way. It's more like the asymmetry operators associated with that system are intensifying because the system is undergoing a dynamic change relative to the invariant background. Think of it like this. The hypergravity field is this perfectly stable, coherent background. An object at rest, or moving at a constant velocity, maintains a steady level of coherence with it. But when you push on it, when you apply a force and make it accelerate, you're shaking it up relative to that stable background. You're disturbing its connection. That disturbance, that loss of alignment or phase lock with the fundamental field, is what manifests as increased variance. And we observe that variance as, well, increased apparent mass, as time phase variance, which looks like time dilation, and other effects the paper calls relativistic residues.
Wow, okay. So that mass increase we see in particle accelerators, where particles get incredibly heavy and hard to push faster as they get close to C, that's not just some weird consequence of speed itself or space-time geometry doing funny things. It's a residue of coherence degradation. It's a direct physical result of the particle's connection to the fundamental hypergravity field being messed up, being degraded by the intense acceleration. That has a huge reinterpretation. It makes it sound much less weird, almost more mechanical.
Exactly. It grounds it in a physical process related to the field interaction. The paper even formalizes this with a relationship it calls the mass incoherence derivative relation. Basically, it says that how much the mass changes as you accelerate, proper acceleration, is directly proportional to how much the incoherence changes as you accelerate, incoherence index, proper acceleration. Put simply, the faster you accelerate, the faster your apparent inertial mass grows, precisely because you are losing coherence with the fundamental field at a faster rate. It's a direct causal link. The resistance you feel when you try to accelerate something isn't just its innate laziness or inertia, it's partly the resistance arising from disrupting its fundamental coherence with the universe.
Let's try another analogy for everyone listening. Imagine you've got a perfectly tuned radio antenna, right? Locked onto a really clear signal from a powerful station that's full coherence, C1. Now imagine you start shaking that antenna really violently. You're accelerating it back and forth. What happens? It starts to lose the signal, right? The reception gets staticky, maybe cuts out altogether. It's losing coherence with the broadcast source. The mass increase in this picture is like the resistance you feel trying to shake it. The harder you shake, accelerate, the more you disrupt its connection, lose coherence. And maybe the heavier or more resistant it feels to further shaking. It's not the antenna's metal changing, it's connection state degrading. Okay, so that brings us to the big one, the speed of light limit. In standard ASR, mass goes to infinity as your velocity v approaches c. You hit this ultimate speed limit because it would take infinite energy. How does Relativity 2.0 reinterpret that barrier? What happens when an object gets close to that speed c in this new framework?
Right. So in Relativity 2.0, as the velocity approaches c, or more precisely what the paper calls the derived speed scale c star, which is a key difference, something critical happens to the coherence. The coherence ratio approaches 0. This means the system reaches a state of total incoherence. It's completely decoupled from the hypergravity field. Remember our antenna analogy? It's like shaking it so violently it loses the signal entirely. C goes to 0. So the interpretation is profoundly different. Infinite inertial mass expression at light speed isn't because you've hit some absolute kinematic speed limit built into space-time. It's not fundamentally about needing infinite energy just to go faster. Instead, it happens because the system, by reaching that state, is fully disconnected from its coherence origin. There's literally no coupling left to the fundamental hypergravity field H. The system has reached a state of complete asymmetry saturation, total incoherence. Trying to accelerate it further is like trying to push on something that has no connection left to push against. Its resistance becomes infinite because its coupling has become zero. And this brings us to that derived speed scale, C. It's not just the C we know from SR, treated as a universal fundamental constant. The paper defines C as the emergent local light speed value. It's a speed scale that's determined by the specific properties of the coherence field in a particular region or context. Now, in the standard conditions described by special relativity, in the vacuum of our universe, this derived speed scale C just happens to numerically reduce to the familiar value of C. So C isn't the ultimate invariant, it's a derived property. It emerges from the underlying hypergravity coherence field in our specific universe. Much like the speed of sound is a derived property of the air it travels through, not a fundamental constant of nature itself.
Whoa.
Okay.
So the speed of light limit, it's not really a speed limit in the sense of a cosmic speed camera saying you can't go faster.
Yeah.
It's actually a coherence collapse threshold.
Mm-hmm.
It's not about hitting a velocity wall, but about reaching a state where your connection to the fundamental reality just collapses.
Yeah.
Zero coherence. And once C hits zero, the resistance mass goes infinite because there's no connection left. That completely reframes one of the absolute pillars of modern physics. It's not kinematic, it's ontological decoupling.
It is a fundamental reframing, yes. It shifts the nature of the limit from an external constraint imposed by space-time geometry to an internal state transition of the system itself. It's complete decoupling from the hypergravity coherence field. It suggests C is a consequence, not the ultimate cause.
Now, what I find really neat, maybe even elegant about this Relativity 2.0 idea is that it doesn't just toss out 100 years of physics math. The paper makes a point of saying it preserves the mathematical form of special relativity's transformations. So the equations physicists use every day, they often look the same or very similar. But the meaning, the physical interpretation of what those variables represent changes completely. Is that right? That sounds like a clever way to build on existing work rather than just replacing it.
That's exactly right. It's a very clever and, I think, strategically important aspect of the framework. It provides mathematical continuity. The core equations often retain their familiar structure, which means the existing mathematical machinery of physics doesn't need to be discarded wholesale. Physicists could, in principle, adopt this framework without relearning all the math, but they would need to apply a profound reinterpretation to what the symbols mean. The physics changes even if the equations look similar. It shifts from pure kinematics to coherence dynamics. Take the Lorentz factor, gamma, gam. In SR, mathematically, it's Pauli, so 1 divided by the square root of 1 minus v squared over c squared, right? Gam minus v squared over c squared, right? Gamma towards 1 tast v sans c. Now notice the shift. In SR, the velocity v is the input variable that directly drives gamma. Faster v means bigger gamma. In Relativity 2.0, the coherence ratio c is the input variable that drives go c. Lower c means bigger gam. And here's the really important expansion. C itself isn't just determined by velocity. Yes, velocity can affect it via acceleration-induced incoherence, but C can also depend on acceleration directly, on local field conditions, maybe even on quantum gravitational effects we don't fully understand yet. So C is a much richer variable than just V. It reflects the system's overall coupling state to the fundamental hypergravity field. The core equation for mass really illustrates this beautifully. Mass, let's call it MC, to show its dependence on coherence, equals the rest mass mu divided by the coherence ratio C. So MC is MC. Look how that plays out. When an object is at rest, we assume it's in full coherence. So C1, then M1, 1 M, its mass is just its rest mass. Perfect. As the object approaches conditions where its coherence drops towards 0, maybe due to extreme acceleration approaching C, then its mass MC, M0, approaches infinity. This gives exactly the same mathematical result as SR's mass increase equation, where S of V. But the reason is totally different. It's grounded in coherence collapse, not just hitting a velocity limit where up del blows up. It gives a physical mechanism for the mass increase. Decoupling from the hypergravity field.
Okay, putting these side by side is really helpful. Let's do that explicitly. Walk us through a few key relativistic effects and contrast the standard SR interpretation with this new Relativity 2.0 hypergravity coherence model. This should really highlight the differences in detail.
Great idea. A direct comparison really makes the paradigm shift clear. Let's go point by point. First, the rest state. In standard SR, at rest just means an object isn't moving relative to your chosen inertial frame. It has fixed space-time coordinates. It's purely kinematic. In Relativity 2.0, the rest state is reinterpreted more deeply. It's an object in full coherence with hypergravity invariance, C1. There's no asymmetry causing variance, no disruption. Its connection is perfect. So the key shift is defining the state not just by its space-time frame, relative motion, but by its coherence frame, its coupling state. Next, acceleration. In SR, acceleration is just a change in velocity. This change, via the Lorentz factor, causes changes in measured time and length. It's a direct consequence of relative motion changing. Relativity 2.0 reinterprets this fundamentally. Acceleration increases in coherence relative to the hypergravity field. The asymmetry operators associated with the system intensify, actively disrupting the coupling. So the key variable driving the effects shifts from velocity itself to the resulting coherence deviation. Acceleration causes coherence loss, which causes the effects. How about mass increase? SR says mass increases with velocity, mv dot, consequence of the object's relativistic energy and momentum. It appears heavier. Relativity 2.0 gives a causal mechanism. Mass increase is a residue of coherence degradation. The resistance to acceleration, inertial mass, goes up because the system's coupling C to hypergravity is weakening. The math looks similar, MEO, where 1C parallels SIG, but the driving variable shifts from the Lorentz factor kinematic to the coherence ratio C and its inverse, the coherence gamma yay ontological coupling state. Okay, time dilation, this is a big one. SR says moving clocks literally tick slower because time intervals themselves change with velocity due to the structure of space-time. Time slows down for the moving observer. Relativity 2.0 offers a drastically different picture. Time shift is seen as phase decoherence between the moving system's internal processes and the underlying rhythm of hypergravity invariance. Critically, ontological time itself isn't slowing down. The universe's clock ticks the same for everyone. But the moving system's internal clock is falling out of sync, losing phase with that universal rhythm, making it appear to run slow from the outside. It's not time bending, it's the system's internal rhythm degrading. The key variable shifts from space-time distortion to coherence phase variance. Then the speed of light limit. As velocity v approaches c, the Lorentz factor barrier goes to infinity. Reaching c requires infinite energy. It's a hard kinematic speed barrier, relativity 2.0. As velocity approaches c, or c, the coherence c approaches zero. This means complete incoherence, full asymmetry saturation. The inertial mass diverges because c is zero, the coupling is gone. The limit shifts from being a velocity barrier, you just can't go faster, to a coherence collapse threshold. You lose fundamental connection. And finally, the underlying constant. In SR, the speed of light c is the invariance, Lorentz invariance. It's the fixed measuring stick of the universe. In Relativity 2.0, hypergravity invariance, h, is the true fundamental constant. The speed of light c is not fundamental. It's a derived property that emerges from the coherence field in our specific universe. A fundamental shift from a speed constant defining the rules to an ontological constant h being the source from which rules like the value of c emerge.
Looking at it like that side by side, what really jumps out at you, for me, it's that shift away from time literally slowing or space literally stretching. The idea of phase decoherence instead of time dilation or coherence degradation causing mass increase, it feels less. Well, mystical, like you said earlier, makes these weird relativistic effects feel like tangible outcomes of how well a system is connected to its fundamental field, H. It grounds them in a mechanism, rather than just saying that's how space-time works.
I completely agree. What stands out most for me is exactly that gain in ontological clarity. It feels like it resolves that relational mysticism we talked about. By moving the true invariance from H, which, as we've seen, this paper argues, is a derived quantity, an effect to hypergravity coherence, H, the proposed underlying cause, Relativity 2.0, provides a much clearer, more satisfying causal chain. We're no longer just saying, well, space-time has to warp this way to keep constant. Instead, we're potentially saying things appear to behave this way because their interaction with, in coherence relative to, the fundamental hypergravity field is changing due to acceleration. It turns these kinematic effects into potentially measurable properties of an underlying field, and that's huge, not just for understanding, but because if it's a field property, maybe you can interact with it. Maybe you can engineer it.
Right. And that brings us to the mathematical stage for all this. If Minkowski spacetime, with its nice flat grid, was perfect for SR's story of relative motion, then this new story, Relativity 2.0, with all its talk of coherence dynamics and layers of reality, it needs a different kind of stage, right? And the paper says that stage is the Finsler coherence hyperfractal phase space, FCHP. Okay. It's quite a name, sounds incredibly complex. Can you help us visualize what FCHP is conceptually and why it's the right mathematical home for this theory?
Yeah, FCHP is definitely a more complex mathematical beast than Minkowski space, but it needs to be to properly capture all these new ideas: coherence, asymmetry, hypergravity, emergence. Think of Minkowski spacetime in SR as, like you said, a smooth, flat grid. Distances and time intervals are measured pretty consistently regardless of your direction or speed once you account for Lorentz transformations. It's isotropic and homogeneous, basically the same everywhere and in every direction, like a perfectly flat, infinite sheet of graph paper. FCHP, on the other hand, is a much more generalized kind of mathematical space, specifically a phase space geometry. It's designed to handle more complexity right from the start. First, it naturally incorporates anisotropy. That means its properties can depend on direction. Unlike Minkowski space, where moving east is geometrically the same as moving north, in FCHP, the geometry or the rules of movement can be different depending on your direction of motion or acceleration. This is crucial because Relativity 2.0 suggests coherence coupling might not be uniform. It could vary depending on how you're moving relative to the hypergravity field. Second, FCHP has this concept of hyperfractal layering. This is where the paper's multi-tiered ontology gets built right into the math. It means the geometry itself can have different levels or strata. Physical effects might manifest differently depending on which layer of reality or which coherent state a system is in. Imagine trying to map a complex mountain range that's also like a fractal. The terrain, its steepness, how easy it is to move, changes not just with your location, XYZ, but also maybe with your altitude or the way you're moving through it. Minkowski was the flat plane. FCHP is that complex, layered, anisotropic mountain. And third, crucially, FCHP is designed to directly integrate coherence gradients. The degree of coherence, that value C from 0 to 1, isn't just some external number you plug in. It becomes an intrinsic part of the geometry itself. The landscape of FCHP literally changes shape depending on the local coherence state.
So it's not just a passive backdrop like the graph paper. It's a dynamic stage, purpose-built for a theory based on varying coherence, layered reality, and direction-dependent effects. It sounds like the perfect fit for Relativity 2.0.
Exactly. If Minkowski space was the natural language for SR's focus on constancy and relative motion, FCHP is the natural language for Relativity 2.0's focus on hypergravity coherence, asymmetry, and emergence. Within FCHP, there's something called the Finsler metric. It's a more general way to measure distances and paths than the simple metric used in Minkowski space. Relativity 2.0 redefines what makes this metric invariant. It says the fundamental distance or path interval isn't defined by keeping ρ constant, but by maintaining coherence with hypergravity. And that inherent anisotropy of Finsler geometry, it now gets a physical meaning. It represents the anisotropy of coherence coupling. How strongly you're coupled to the hypergravity field might actually depend on your direction of motion or acceleration state. This leads to a really key mathematical insight. In FCHP, coherence itself becomes a geometric scalar field. This means the coherence gradients, the changes in C across the space, are directly woven into the fabric of the metric. When those asymmetry operators kick in, like from acceleration causing incoherence, they correspond to specific path-dependent changes in the coefficients of the Finsler metric. The geometry literally responds to changes in coherence. And the upshot is pretty amazing. The coherence ratio C basically becomes a field value at every point in this complex FCHP space. Like a temperature map, but showing coherence. This means all the variants we observe, time dilation, mass increase, Doppler shifts, they all become direct readouts of this coherent scalar field at that point in the hyperfractal phase space. They are manifestations of the geometry itself, which is in turn shaped by coherence.
So it takes those effects that felt a bit mystical in SR spacetime, just stretching, and grounds them not just in a field concept, but embeds that field directly into the geometry of this more advanced phase space. It makes relativistic effects less about kinematics and more like intrinsic field theoretic properties of this hypergravity coherence field, expressed through the FCHP geometry.
That's a huge conceptual shift from abstract distortion to something potentially measurable and mappable within a field.
It absolutely is. It provides a much more concrete, potentially causal mechanism built right into the mathematical structure. And that structure, because it relates coherence to geometry and observable effects, opens the door to thinking about practical applications.
And yeah, this is exactly where it gets potentially world-changing, right? If all those relativistic headaches, mass ballooning, time slowing down are really just symptoms of coherence loss, then the obvious next question for any engineer or scientist is, can we stop it? Can we actively prevent that coherence loss? Can we accelerate without losing coherence? That sounds completely revolutionary. It really does. And this is probably the biggest, most exciting potential payoff that Relativity 2.0 offers, a new engineering lever. Standard SR basically says those effects are unavoidable. They're built into the rules of spacetime. You accelerate, you pay the relativistic price, period. But Relativity 2.0 says, wait, Those effects are contingent on losing coherence, and if something is contingent, maybe it's not inevitable, maybe it can be influenced, managed, counteracted. The paper formalizes this idea by introducing an active restoration term, let's call it R, into the equation, describing how coherence changes. Conceptually, the equation looks something like this. DCD is ACCOFO plus ER. Let's quickly break that down. DCD is how fast coherence changes over time. The first part, COFO, shows that acceleration naturally decreases coherence. The faster you accelerate OFO, the faster you lose coherence. That's the minus sign. COPO-CO is just a constant saying how strong this effect is. But the second part, plus ER, that's the new idea. It's a term representing an active process designed to restore coherence. R could be, well, we don't know exactly yet, but maybe some kind of phase locking mechanism tuned to the hypergravity field. Maybe some form of coherent shielding. Or quantum techniques to rephase the system. Lambda is just how effective this restoration method is. Now, here's the monumental implication. If you can engineer a system where this restoration term actively cancels out the acceleration-induced incoherence, so if R is roughly equal to comma, then the net change in coherence, DCB, could be close to 0. Coherence C would remain stable, close to 1, even while you're accelerating intensely. And if C stays near 1, what happens? Relativistic mass growth, MMC, stays minimal. Time shift, related to phase decoherence, also stays minimal. These effects could potentially be suppressed during acceleration.
That sounds like the absolute holy grail for space travel. It implies that going really, really fast, near STRI, might not automatically mean insane energy costs due to runaway mass, or crews experiencing centuries passing back home for every year they travel. If you can maintain coherence while accelerating, maybe using a trajectory that follows what the paper calls a coherence-preserving submanifold, then maybe interstellar travel becomes vastly more feasible. Imagine a ship where the mass doesn't balloon towards infinity and the crew's clocks stay reasonably synced with Earth's. That changes everything. That's warp drive territory almost.
Well, maybe not warp drive in the classic sci-fi sense, but certainly a fundamental shift in overcoming relativistic barriers. And the potential implications ripple out far beyond just propulsion. First, mass and inertia control. If mass increase is tied to coherence loss, then actively managing coherence could, in principle, allow for dynamic control over inertia itself. Maybe making things easier to accelerate or decelerate. Maybe inertial dampeners, like in sci-fi, to protect against high G forces. It opens up theoretical possibilities. Second, quantum computation and information. This could be huge. Quantum computers rely utterly on maintaining quantum coherence. Decoherence is the enemy. If these principles of hypergravity, coherence, and active restoration apply at the quantum level, perhaps they could lead to ways to dramatically extend qubit lifetimes, making quantum computers much more robust and powerful. Or maybe even enable totally new quantum computing paradigms based on manipulating coherence directly. Third, advanced navigation systems. If coherence is a fundamental property you can potentially measure and control, you could imagine navigation systems that use this information for incredibly precise maneuvering, especially in deep space or complex gravitational environments, perhaps allowing for more efficient trajectories by surfing the hypergravity field, in a sense.
It's really mind-blowing stuff. This isn't just tweaking equations. It's proposing a fundamentally new understanding that comes with a potential toolkit for manipulating reality in ways we haven't even conceived of before. It's a blueprint for experiments, maybe even for technologies that sound like pure fiction today. But how do we know if it's right? How do we test it? What are the concrete near-term signals we could look for in a lab that would tell us if Relativity 2.0 is on the right track and actually different from standard SR?
That's the crucial question, and the paper doesn't shy away from it. It proposes several concrete, near-term experimental tests designed specifically to differentiate its predictions from standard SR. These aren't just vague ideas, they're specific setups. One key proposal is using twin accelerometers. You take two identical, extremely precise systems, maybe advanced atomic clocks, and accelerate them in exactly the same way. But on one system, the test arm, you apply whatever technique represents that coherence control term, R0. The other identical system, the control arm, gets accelerated the same way, but without the active coherence control, R0. Relativity 2.0 predicts a clear difference. The test arm with coherence control should show less clock dephasing, less time dilation, and a lower effective inertial mass, less relativistic mass increase, compared to the control arm, even though both underwent the same acceleration profile. Standard SR would predict identical results for both. That's a direct, measurable test. Another approach involves storage ring ions. Similar idea. You accelerate two identical bunches of ions in a high-precision storage ring using the same acceleration ramp. To one bunch, you apply some kind of phase-locking field designed to maintain its coherence. Relativity 2.0 predicts this bunch will show a reduced spectral shift compared to the control bunch. It's like a coherence-preserved Doppler effect. SR would predict the same shift for both bunches under the same acceleration. And a third example is using a matter interferometer. These devices split particle waves, send them along different paths, and look at the interference pattern when they recombine. If you subject such an interferometer to pulsed acceleration, Relativity 2.0 predicts that without coherence control, R0, the interference visibility will drop due to decoherence in a way that scales with acceleration squared. But if you apply active coherence control, R0, during the acceleration pulse, the prediction is that the visibility drop should be flattened or significantly reduced. The coherence is preserved, so the interference pattern stays clearer. Again, a quantifiable difference from standard expectations.
Okay, so these are real, tangible experiments with clear, falsifiable predictions. They directly pit Relativity 2.0 against standard SR. If those experiments show less clock dephasing, lower mass increase, or preserved interference under acceleration with the R term active, that would be monumental evidence. That's how science progresses, right? New idea, testable prediction, rigorous experiment. So as we wrap up this deep dive, let's try and bring it all together. We've journeyed through Relativity 2.0, this really audacious, incredibly detailed proposal for upgrading special relativity. It's not about throwing Einstein out, we stress that. His math describes what happens incredibly well. This is about potentially understanding why it happens on a deeper causal level. We've moved from ideas like relational mysticism and space-time literally bending to a picture where relativistic effects emerge as consequences of a system's coherence or its lack thereof with the proposed fundamental hypergravity field.
Exactly, and the beauty is, as we discussed, the mathematical form of SR is largely kept intact. The Lorentz factor finds its parallel in the coherence gamma 1c. This means decades of physics aren't invalidated, but the meaning behind the math gets profoundly reinterpreted. It aims for a cleaner ontology, placing the true ultimate invariance not in a derived speed like c, but in this deeper hypergravity coherence field, h. It tries to make the why behind relativistic effects more transparent, potentially linking them to a manipulable field property rather than just an immutable spacetime structure.
And crucially, this isn't just armchair philosophy, it's pointing towards action. It offers concrete ways to test its claims, those twin accelerometers, the ion rings, the interferometers. And it dangles this incredible prospect of maybe, just maybe, developing coherence-preserving acceleration systems, technologies that could mitigate relativistic mass growth and time dilation, potentially rewriting the future of space travel and maybe much more. It's a shift from just observing the rules to maybe learning how to bend them. So for you, listening right now, here's a final thought to chew on. If inertia, if mass itself is really just a residue of coherence degradation, just a symptom of losing connection to the universe's deepest reality, what does that truly imply about the nature of matter? Is matter less solid and more relational than we thought? And if we can learn to actively restore coherence, to strengthen that connection even under stress, does that mean the limits of physics as we know them aren't absolute walls, but more like tunable parameters? Could we be heading towards a future where reality itself is more malleable, more engineerable than we ever dared to imagine? We've really only skimmed the surface today. The paper itself goes into far more mathematical and conceptual detail. But what surprised you the most about this? What new questions does it spark for how you see the universe? We definitely encourage you to keep digging, keep asking questions, keep diving deep.